Well, dear, welcome back. So, how are you doing today? So, as I promised, we are going to discuss the second order system and its application. And as an engineering student, you perhaps seen, or if you have not already seen, you will see in future that second order system has enormous applications. Okay, and it has the capability of modeling many dynamic system. At least the basic model it can provide you. And in that context, I told you earlier that suppose I I am trying to model a second order. I am trying to describe a second order system with the help of a mass spring damper system. Okay, so this mass spring need not be real mass spring, but they can be modeled. Many system can be modeled as a mass spring damper system, right? And we have told you that how to get that equation of motion. Okay, so say this is spring constant, this is damping coefficient C, and then our equations of dynamic equations were plus Cx plus Kx equal to 0, provided that there is no other externally active force which is acting on the system. And how we derive this dynamic equation, that you can refer my earlier lecture using D'Alembert principle, uh, and uh, transferring this system into a virtual static system, and then actually applying the static equilibrium condition, we obtain this. Now, how to solve this equation? Before telling you that story, first we'll learn how to actually solve a, much simpler system. Okay, suppose I do not have a damper. Instead, I have a mass spring system. So it has a spring simply, and a mass is hanging from the spring, and spring has a stiffness constant K. So as you can see that mx dot plus kx will be actually equal to 0, will be the dynamic equation, right? So there is no damper. So and the remaining other part, how we derive this and etc remains the same as we have discussed earlier. That is apply D'Alembert principle, draw the free body diagram for those who actually are seeing this for the first time. So I will tell you, this is a inertial force, and we are considering here a single degrees of freedom system. Okay, single degrees of freedom system. X is the displacement. So this is simply spring force, this is inertial force, and this is the dynamic, this is the virtual static, the system is in virtual static equilibrium condition, and we have ignored G because G has no role to play except shifting the mean position of equilibrium. That we have observed in my earlier lecture. Okay, so G will simply actually what is your physical interpretation of this such system? Physical interpretation is, if I perturb in this direction or in this direction, then there will be oscillation. Okay, that is the mass will oscillate back and forth, back and forth, back and forth. And let us try to only use this intuition and try to understand how such system dynamic equation can be solved. Okay, so first of all, this is called the homogeneous. This is homogeneous linear differential equation. okay, with constant coefficient. Right, with constant coefficient. But that means A and K, they do not change with time, right? And such systems are actually called time invariant system. I have already explained time invariant system. Time invariant system means with respect to time, with time this A and K, this is called system parameter, and X is called state parameter, okay? So this system parameter are not changing with respect to time. That's why they are called time invariant system. But in all system modeling, this need not be so, because you see, in case of a missile, for example, or in case of a aircraft which has during takeoff certain mass, and then as it goes, masses reduces like that. So this is not the model of that kind of system. Then, so how to solve this differential equation? You see, differential equation solving is not easy. There are some trivial method which may not be applicable in many in solving many system. Why it may not be applicable? Because they will be complicated to apply for solving such differential equation. The best way of solving differential equation, I believe, is actually try to, through intuition, try to discover rather than derive the solution, okay? So solution should be discovered based on the system for which you are going to solve the differential equation. Discovered rather than derived. Okay. Now, in order to satisfy, and what is the meaning of solving such differential equation? Meaning is very simple. That means what we are trying to do, we are trying to understand with t how the system will change its position. Means at what time system will be where. So that if I solve this, you will obtain. Now, in doing so, first of all, I will have to understand that if I just perturb, it will oscillate, right? Back and forth, back and forth. So the motion will be oscillatory in nature. Okay, that's first observation. So if it is oscillatory in nature, how can we find a solution? Say my solution could be either some kind of sine or cosine term, okay? Because sine and cosine both will be actually returning oscillation, okay? So that I know. And since it is homogeneous linear differential equation with constant coefficient and it's a second order, I also know that there has to be two constant. So what if intuitively I figure out that this is a solution, okay? Now the another requirement is, if this is a solution, then this must satisfy this equation, right? This must satisfy this equation, okay? That means if I differentiate it with respect to time, so this will be negative b sine omega t, and then double differentiate it minus cos omega t. You see, minus, if we just see A sine omega t plus B cosine omega t. So you see this second derivative actually is returning the trial solution. We call it trial solution. Means we are just making trial. We have made an assumption that okay, the system is like this, oscillator in nature, and my solution could be this. I guess a trial. And the one fundamental requirement is that there should be two constant because it's a second order system. Okay, and you see double derivative has to return this. Okay. So this, how about E and B? E and B are two constant. Okay, where A and B are two constant whose value should be determined from some initial conditions. Which are to be given. Okay, and this is very, very logically doable things. That means if I can, if I see, okay, at t equal to 0, that means x say equals to x0. Means at t equal to 0, system started from somewhere. Okay, say I have stretched it at some value which is x naught. Okay, and then I have allowed it to oscillate. So initially there should be some displacement, and say initially also because I stretched with some velocity, say at t equal to 0, the initial velocity is this. So these are the given. If they are not given, E and B cannot be explicitly find out. Okay, they are to be given. They are called initial condition or boundary condition. Now once they have given, I can just go ahead and try to find, simplify the solution, sine omega t plus B cosine omega t. By the way, this omega t, what is omega t actually? Omega t has very interesting interpretation. So I am writing this equation in a simple form like this: k by m x equal to 0. So x double dot plus omega square x equal to 0, where omega is equals to of root over of k by m. So you see, incidentally, omega is called the system's natural frequency. System's natural frequency. Why it is so called so? Because frequency with which this mass will oscillate when it is hanging with a spring will depend on only two things, which is the nature of the system. That means how stiff the spring is and how big the mass is, and nothing else, you see. That means, you see, if the spring is sluggish, then if I just perturb, the oscillation will be like this. Okay? And again, if the spring is very stiff, the oscillation will be like this, okay, if I perturb. Or if the mass is too big, then again the oscillation will be sluggish, okay. And if m is too small with the same stiffness, so oscillation will be very quick, like that, okay. Intuitively, this depends on system's nature. That's how stiff the spring is and how big the mass is. That's the reason it is called system's natural frequency. Means if I perturb with a system which has unique m and k, the system will have only unique natural frequency, and it has so many intuitive implications afterwards we'll see in design. Okay, it's very important to figure out a system's natural frequency, right? The reason is the system will oscillate using that frequency only. And why it is omega? You see, it's called circular frequency. System's natural frequency is circular frequency. Well, wait a minute. I see I have perturbed m in this direction x, and it is oscillating in this direction only, back and forth, back and forth, back and forth. So where is omega, which is a circular frequency? Perhaps many of you know. Those who do not know, try to understand. Suppose we are considering a circle called reference circle. Reference circle. And let us assume that a particle is tied on a string of this reference circle, and I am rotating the particle like this, okay, around the circle. This is the diameter. Now, the particle at the initial stage, say it was here, and then it was here, and then it is here, then it is here, then it is here, as the rotation is taking place in this direction. Okay, is it clear? So here, now, what is the motion of the feet of the perpendicular drawn on a diameter, okay, of this particle? Actually, that motion is this motion which you are observing here. Okay, so let us try to understand this with horizontal diameter. So feet of the perpendicular, the distance was this radius initially when it was at this stage 1. When in 2 stages, so feet of the perpendicular is this one. Okay, at 3 stage, feet of the perpendicular is this one. 4th stage, the feet of the perpendicular is this one. 5th stage, feet of the perpendicular. So, and then again, you see 6th, 7th. So, again it is here 8, 7, 8, 9, 10 feet of the perpendicular. So I am interested to see the feet of the perpendicular. What is the motion of the feet of the perpendicular? So as the particle is rotated in this reference circle, you see feet of the perpendicular actually is oscillating along a diameter. And by the way, here in this particular example, okay, so my figure corresponding to this reference circle could be like this. Same figure. Okay. So in this direction x, I perturb, and then it is rotating this direction. So, and how fast I am actually rotating the particle is actually governed by frequency. What is the frequency? It's just, this is the circular frequency omega. You see, circular frequency, or that's why it is called actually, unit is also radian per second. That means how much angle the particle is subscribing at particular time. Okay, so that's the circular speed of the particle. We call circular frequency is radian per second unit. So it's not hertz because it is omega. And now, what is the implication of omega? I think you know. Okay, this is called frequency, but it is circular frequency. Circular frequency of what? Not this body, but a fictitious reference circle. You consider reference circle. You consider a particle tied up with a string, and you are rotating that particle along that circumference of the circle. Now, omega is the speed of rotation of that particle along the circumference of the circle. So that's why it is called circular frequency. Okay. So you see, this is real form of omega, right? Now let us try to go ahead and solve this equation. Okay. So this can be actually simplified in this form of substitution. Incidentally, this is very, very common in robotics. You have already used it during your inverse kinematic solution. This is called separation of variable principle. That means I can substitute A equal to some constant C cos phi, and substitute B equal to constant C sin phi, where phi is a constant, C is a constant, and phi is called incidentally phase angle, which we'll discuss later on. So what we are trying to do, instead of sine, cosine, etc., now we'll use only one transcendental relation. So if I just put it, then x will be equals to C sine omega t plus phi. So where from it is coming? You just put it here. So C, so I have just jumped a step, but I understand you have already accustomed with such simplification. Plus okay, and this is actually equals to C sine of, and this substitution I have made, and I can express A and B in terms of these two imported constant. Okay, so you see what is C? C is nothing but root over of a square plus b square. And what is phi? Phi is nothing but tan inverse b by a, isn't it? Tan phi equals to b by a, so phi equals to tan inverse this. So they are related. Okay, this substitution I have made. However, the two constant I have imported, where c and phi. Why I have done it? Because you see, instead of sine and cosine, I have simplified. Okay, that some constant in sine. Okay, some substitution you can do. A equal to c sine phi, b equal to c cos phi, and then you can land some cos in terms of cos. Okay. So I have these two initial boundary condition which are given. Okay, so you see, I need to figure out using these two equation, one and this one and this one. Okay, I will figure out what will be my x naught and x naught dot. Okay, very simple. omega t. So at t equal to 0, this is at t equal to 0, what you have, x naught equal to, this is 0, b, this is 1, right? Cos 0, 1. So you got b equals to x naught. Then to get another constant, I have differentiated this. Right? So this is this relation a omega so at t equal to 0, we have assumed that the velocity was x naught dot. Okay, so this is equals to a, and this is becoming 0 because sine 0 is 0. So from here we are getting two constant. So you see, this is given x naught dot, omega is given the moment I have given you a mass spring system. So in terms of this initial boundary conditions, E and B are obtained. Okay, once A and B are obtained, C is obtained. And once C is A and B is obtained, then phi is also obtained, right? So amplitude, so x will be, solution will be x sine omega t plus, so I am going to show you every detail, right? So that you, so C instead of C I am writing x, okay? And this is my general solution, where each and every term is known to me. You see that x dot C, or whatever you call it, equal to C equals to root over of a square plus b square. In terms of given boundary condition, a square means okay, plus x naught square, and phi equals to tan inverse, okay, x naught divided by, okay. So you see that we are able to find the solution for the simple second order linear differential equation having only mass and spring. And we'll study this solution, and in the next lecture we'll see, pictorially we'll see that what will be the nature of oscillation, that means x versus t, x dot versus t, x double dot versus t. All this pictorially you can draw from here, okay? And we'll draw it and we'll see that how I can obtain a solution for such a simple but not so simple mass spring model. The same exercise can be done using another example, another model, which is also will show the similar behavior. So if I try to draw now, so what will be, you can see, so phi is the phase angle. That means it has some so it will go on oscillating like this. Okay. Uh, okay. So you see the way this will, okay, it is the amplitude of oscillation, which is x. This is actually your phi. That is the phase, and this is the, you see the initial at t equal to 0, it was at x0, so all kind of thing. It will be a little bit, okay. So we'll draw a bit more beautifully. So this is actually this solution of the second order differential equation. That means x versus t you are getting, okay, as a result of this solution. So we'll continue our discussion with this very simple example, and slowly we'll see what are the complications when this simple mastering model is excited by an external force. All these very interesting things we will study, okay, subsequently. Okay. Till then, have a nice day. Stay safe. Bye bye.